Tonight on The Sky at Night, we're going interstellar.
Travelling to the stars has always seemed like an impossible dream. But now some scientists believe that it may be possible within our lifetimes.
And that prospect has just become even more enticing because we have a target to aim for. Within the last few weeks, astronomers have announced the discovery of a hospitable planet around the Sun's nearest neighbour, Proxima Centauri.
On tonight's programme, we'll be finding out how this new planet was detected and why it's such an important discovery.
And Guillem Anglade-Escude will be exploring the revolutionary new technology that might take us deep into space.
Welcome to The Sky at Night. On August the 24th, astronomers made an extraordinary announcement.
Now, scientists are hailing a major discovery, a new planet which they've called Proxima b. At just 4 light years away, it's relatively close to us. It's roughly the same size as Earth, and because it's just the right distance away from its star, it could be the right temperature to have liquid water and possibly life.
Over the last few years, we have identified over 3,000 planets orbiting other stars. But this one is special. It's already been called one of the discoveries of the century. So what makes this planet such an enticing target for our first interstellar mission?
Proxima b is in orbit around Proxima Centauri, the closest star to our Sun. Only discovered in 1915, Proxima is an apparently unremarkable star. It's the smallest of the 3 stars that make up the Alpha Centauri system. A red dwarf, like 70% of the stars in the Milky Way, is just 12% of the mass of the Sun. That small size means that the pressure and the temperature at the core are much less than in our Sun, and so the processes of nuclear fusion that power the star proceed much more slowly. And so, Proxima Centauri is cool. Its surface temperature is only half that of the Sun, and its luminosity is 500 times lower. In fact, it's so dim that even though it's the closest star to us, it can't be seen from Earth with the naked eye. But the discovery of a planet around Proxima Centauri makes it a much more exciting neighbour. This is the paper published in Nature just last month that announced the discovery of the planet that the team called Proxima b. And I've come here to Queen Mary University of London to meet Guillem Anglade-Escude, the leader of the team that made this remarkable discovery. Anglade was part of a project called the Pale Red Dot that used the European Southern Observatory's telescopes in Chile to observe the star for 60 straight nights last spring. But it's only now, after careful analysis, that the results have been released. Congratulations. It's a wonderful, wonderful discovery. But how on earth do you tell that this tiny planet is there going around this star?
Well, that took some time. It was not something that happened from one day to the next.
But I think the thing that's difficult for me to get my head around is I sort of imagine you taking a picture and looking for the planet in the image, but that's not how it works.
No, not in these cases, and most of the planets don't work this way because the planets are very faint compared to the stars. So what you see is the star, and we are using a method that is indirect. So we see what the planet is doing to the star, because the planet and the star both have mass, and therefore they attract gravitationally, and the planet going around the star moves the star itself, and that's what we are trying to measure.
I was going to say, because the planets are small compared to the star, so this motion must be very subtle. Like for example, the Earth can't have much effect on the Sun.
The effect of the Earth on the Sun is small. It's about 10 centimeters per second. So you can think that just moving like this, like an ant. For planets around stars that are much smaller, like Proxima, the star is smaller, so the planet is making the star move more. And in that case, the motion is about meter per second level.
Hang on, so you're able to detect that a whole star is moving at a meter per second, which is that's sort of walking pace.
Exactly, and it's not the trivial thing to do. because what you have is the planet going around the star periodically, and we see this motion going up and down, up and down. So you see a wave, like something like this.
And that's the signature that tells you that there's a planet there.
When you see something like this on a star that repeats over time, that is always consistent, and a number of other things, this is when you are convinced that you have a planet around the star.
Excellent.
Yes.
And then from there, the next question is, what do we know about this planet? What can we tell other than the fact that it's there and it's making the star move?
So just from the motion that we detect, this sinusoid, this curve, this oscillation, we know the period.
And so for this planet, what is that number?
It's 11.2 days.
So it's going around pretty quickly.
Yes. From that, we can infer the distance between the star and the planet.
Just from knowing how gravity works, basically.
Yes. This is Kepler's law, the first Kepler's law.
And so what is that separation for this planet?
In this case, is around 5% an astronomical unit.
Okay, so that's what? That's something like 7.5 million kilometers, something like that.
You're faster than me.
Yeah.
Yes.
Okay, but it's very close to the star, right? That's much closer to the star than Mercury is to the sun.
Yes, it's about it's a tenth of the distance between Mercury and the Sun. And the other thing that we get from this curve is the mass of the planet.
And what is that mass?
This mass is 1.3, 1.4 Earth masses.
So for this system, we've got a 1 1/3 Earth mass planet going around its star every 11 days. Mm-hmm. So just thinking about it, I expect that's much closer to the star than Mercury is to the Sun. So I'd expect that to be hot.
Yes, that you would expect that to be hot if that was the Sun. But this is Proxima, and it's a red star. It's a red dwarf, and it's a small red dwarf. So Proxima has around 12% of the mass of the Sun. So this means that if you want to keep warm, you have to be much closer to the star.
Right.
And this is when then the magic happens, where you put all the numbers together. Then you can estimate how much light, how much energy is reaching the planet. And this amount of energy is about 70% the amount of energy that Earth is receiving from the Sun.
So it's actually pretty warm by planetary standards.
By planetary standards. The next calculation you can do is try to estimate the temperature that this planet would have. And you do the numbers and you get 240 kelvins.
Because what, minus 30
Minus
centigrade?
30, minus 40 Celsius, something like this. But you would say, oh, that would be frozen. But the same would happen to Earth. Earth is about 255 kelvins, which means that minus 20 Celsius, and this is not minus 20, right? And what happens there is that Earth has an atmosphere and keeps it warm. So in principle, this planet, if it has an atmosphere, it would have greenhouse effect, and that would keep the planet warm.
So with an atmosphere, it might be warm enough to have liquid water.
Yes, that's also the highlight of the discovery.
Well, it's great to be talking about this. Congratulations again, and I can't wait to see what further research comes out and what else is there. Thanks a lot.
Thank you.
The discovery of a potential Earth-like planet so close to us instantly raises another question. Could we send a spacecraft to visit it?
Everybody ready to say goodbye to our solar system?
In science fiction, interstellar travel always seems easy.
Here we go.
In the film Interstellar, it's simply a matter of dropping through a wormhole.
Maximum warp. Punch it.
In Star Trek, a warp drive is used to bend the shape of space-time.
Compressor.
And in the Star Wars universe, you just need to throw a switch to accelerate past light speed and into hyperspace. But in reality, travelling to the stars has always seemed an impossible dream. Until now. We asked Guillem Anglade-Escude to explain why it's so difficult to travel to the stars, and to investigate the technology that might be about to make interstellar travel possible.
For decades, centuries even, we've been wondering what kind of vast engines will be needed to carry us to the stars.
There's one simple, overwhelming problem when it comes to travelling across interstellar space. As Douglas Adams once said, space is big, really big.
And so far, we've only been able to explore the tiniest fraction of it. The craft that we've sent furthest into space is Voyager 1. Launched in 1977, it visited Jupiter and Saturn before heading for the outer edges of the solar system. Now, nearly 40 years later, it's escaped the solar system and has started the journey through interstellar space. But it has a very, very long way to go to get as far as Proxima Centauri. Any practical mission to the stars would need to get there in a reasonable amount of time, say 20 years. But that means going incredibly fast.
The distance between Earth and Proxima Centauri is just under 4.25 light years. Now that works out at roughly 40 trillion kilometers, or 4 times 10 to the 13. Now, in order to cover this vast distance in 20 years, a spacecraft would have to travel at 20% the speed of light. That's roughly 64,000 kilometers per second. If you compare this with the speed that Voyager currently travels at, a mere 17 kilometers per second. It's this disparity between the speed that is required and what is currently achievable that has always made interstellar travel seem almost impossible.
The biggest problem in reaching the speeds needed for interstellar travel is the sheer amount of energy required to produce the acceleration. The Saturn V was the largest and most powerful rocket ever built. It weighed nearly 3,000 tons, and almost all of that was the fuel required to propel its meager 44-ton payload to the moon. Accelerating a spacecraft to the speeds needed to reach the stars would require much more energy than you could ever produce with a conventional rocket. It would need a completely new type of propulsion system.
In the 1970s, the British Interplanetary Society set out to see if it was possible to design a spacecraft that could travel at 12% the speed of light. Such a craft would reach Proxima Centauri in about 40 years. They called it Project Daedalus, and here it is. It was to be a huge craft, 200 meters long, and to save on the energy of getting it off the Earth's surface, it was to be built in orbit. Now, it will be powered by a nuclear pulse engine using nuclear fusion, a technology that hasn't even been invented yet, but that was seen to provide much more energy than chemical rockets that we use today. Still, to get it up to speed, it would need 50,000 tons of deuterium helium-3 fuel that we stored in these vast tanks. Now, there's not enough helium on Earth for this, so they suggested that helium could be harvested from the surface of Jupiter. Easy, really.
Perhaps, unsurprisingly, Project Daedalus never made it off the drawing board. But more than 40 years later, there's another suggestion. In April, Stephen Hawking and internet billionaire Yuri Milner announced that they were putting up $100 million to develop a new interstellar project called Breakthrough Starshot.
For the first time in human history, we can do more than just gaze at the stars. We can actually reach them.
There are two key features to this new system. The first is that the spacecraft won't be carrying its own engines. Instead, it'll have a sail that is propelled by the force of light.
Released from a launcher in orbit, the spacecraft will be accelerated by the second new concept, a vast array of lasers fired from Earth. Theoretically, the planned 100-gigawatt laser, that's about the same power output as 100 nuclear power stations, could accelerate a spacecraft to nearly a quarter of the speed of light in about 2 minutes.
It would reach Mars in just half an hour. It would overtake Voyager in about 4 days, and it will get to Proxima Centauri in a little over 20 years.
There's only one problem. To reach those speeds, the spacecraft will have to be incredibly light, probably weighing no more than 1 gram. It's not exactly the Starship Enterprise, but what could you achieve with a 1-gram spacecraft? I called up Harvard cosmologist Avi Loeb, one of the scientists behind the project, to find out more.
Avi, this is a hugely ambitious project. Do you really think it's possible?
Yes, we hope that we can achieve the goals of this very ambitious project within the lifetime of our generation. This project is as ambitious as was building the pyramids or building cathedrals in ancient times, You can think of it as the cathedral of our generation. The only difference from past cathedrals is that it reaches all the way out to the stars.
And what about the cost? Presumably this is going to be hugely expensive.
The cost is up to $10 billion, of the order of the biggest science projects that we encountered so far, such as CERN or the James Webb Space Telescope.
A critic will say that's a lot of money to send a 1 gram spacecraft through space. You know, how much science can you do with a 1 gram payload?
Fortunately, these days we can pack a lot of smart electronics into a single gram. If you look at a cell phone and strip it from the protective case and strip it from the human interface, you are left roughly with a gram. And that includes a camera, a communication device, a navigation, all of the ingredients we need in the Starshot spacecraft.
And presumably, if the technology is successful, it can be used for other than just interstellar travel.
Yes, this technology can be used to explore the space in between us and the nearest star. For example, we could search for life within the solar system. It would take us only a few days to reach Pluto, instead of about a decade that it took New Horizons to get there. And so in principle, the technology that we develop will allow us to probe the edge of the solar system within a relatively short time.
And what's the time scale for the project? What happens next?
The first 5 to 10 years will be dedicated to a feasibility study where we will demonstrate the technology of reaching a speed far larger than previously reached with chemical rocketry in a laboratory setup. And after demonstrating that, we hope to expand the system until we reach the final design within about 20 to 30 years from now. Following that, we hope to launch the spacecrafts, and it will take them about 20 years to reach Alpha Centauri and another 4 years for the signal from them to reach us. And so altogether, we hope to get those signals while we are still alive.
I'm the same age as you, so I just hope we're both around to see this project completed and successful in our lifetime. I wish you the very best of luck.
Thank you so much.
Before this system becomes a reality, there are many other technical problems to solve. Like building a material that can withstand a 100 gigawatt laser without burning up. And how to get a signal back from a tiny spacecraft hurtling away from us at 20% the speed of light.
It's an exciting prospect. There are still many practical problems to solve, and it's still hard to believe that it would succeed. But looking at this project makes me realize that something I always thought was unreachable may actually be possible. If it succeeds, it wouldn't just revolutionize space travel. It would vastly increase our knowledge of the universe around us. And who knows, with the will and the money, it may actually happen in my lifetime.
If we do develop the means to travel to the stars, Proxima Centauri won't be our only destination. There are other nearby stars we could visit. Pete has been identifying some of the other potential targets.
Within 15 light-years of the Sun, there are approximately 58 stars in 39 separate stellar systems, each being very different.
This group of stars are the closest to being within reach of an interstellar mission. Many of them are cool red dwarfs like Proxima Centauri, and the more optimistic studies place at least one planet in the habitable zone around each one. One of the closest red dwarfs is Barnard's star. Just 6 light-years away, it has the highest proper motion of any star in the sky. At present, it's well placed in the west-southwest at around 9 p.m, positioned off the eastern shoulder of Ophiuchus. To find it, look for a faint V in the sky known as Poniatowski's bull. Barnard's star sits to the top right. The closest sun-like star to ours is Taurus Ceti. 11.9 light-years away, it sits low in the constellation of Cetus, rising in the east-southeast. and is one of my favourite stars to observe. It's at its highest from 3 a.m. Locate the Great Square of Pegasus, then follow the left-hand side down to a bright star known as Deneb Katos. Off to the left is a quadrilateral of fainter stars, Tor being the southernmost of these four. With a possible system of 5 planets in orbit, including one in the habitable zone, Tor Ceti would make an exciting target for an interstellar mission. There are likely to be unique and bizarre planets in orbit around almost all of the stars in the sky.
And if we could send a tiny probe to just one of these stars, imagine how amazing it would be to be able to look at another solar system at close quarters.
Proxima b is undoubtedly an exciting discovery, but just because it could have liquid water on the surface doesn't mean it's going to turn out like Earth, and it certainly doesn't mean that it will be habitable, because planets in very similar environments can develop in very different ways. Just look at Earth and Venus, twin planets of about the same size and at a similar distance from the Sun, but they've developed very differently. Where the Earth became a warm and temperate world, a haven for life, Venus lost its water and succumbed to a runaway greenhouse effect. Its sulfurous atmosphere heated its surface to more than 450 degrees centigrade. It is completely unsuitable for life. Proxima b might be like Earth, but it could equally well be like Venus, or like something else entirely. And so what can we say about conditions on the planet, and about its chances of being hospitable to life? Yes. Maggie has been talking to expert on planetary atmospheres, Joe Barstow.
Yes. So, Joanna, can you tell me how excited you are about the discovery of this new exoplanet?
Well, I'm incredibly excited. I think this is pretty much going to transform the field that I work in.
So, how is it similar to Earth, or how is it different?
Well, one of the things that we think is the same, based on the mass that's been measured with these new results, is that it's likely to be rocky. And that's a good sign. That means that it should have a solid surface. That means that there should be potential, maybe, for something to live on that surface. The major difference is driven by the fact that it's orbiting much closer to that star, and that introduces all sorts of potential problems. And one of those is that we think the planet is something we call tidally locked. And I have here a very small star.
Oh, yes. A very large planet.
And a very large, not to scale planet at all. So what's happening, because the planet is so close to the star, tidal forces mean that the same side of the planet is always facing the star. So as it goes round the star, it's rotating like this. Its day is actually the same length as its year.
So that's like the moon?
Exactly like the moon. From Earth, we can only see one side of the moon because that's the side that always faces the Earth. And so what that means is that one side is getting all of the light from the star and therefore getting much hotter than the other side of the planet. And that could potentially produce very extreme temperature differences.
So looking at life, how does that impact? Is there any way of evening out that temperature, or do you always have that sort of dichotomy, the hot side and the cold side?
Well, thankfully, if the planet has an atmosphere, then it might help to even out that temperature difference.
The atmosphere actually sort of lets the heat be distributed around the planet?
Yes, basically, it enables the heat to be distributed from what we call the day side, the side that's receiving all the light, round to the night side, and it evens everything out.
What is the likelihood of having an atmosphere? I mean, because it's closer to that star.
Yes, and that is also a bit of a problem. I mean, we want it to have an atmosphere quite apart from the fact that it can even out temperature differences to give any life there something to breathe. And if you're going to have an ocean or liquid water, then you also need to have an atmosphere. But because it's so close to the star, it's possible that it may no longer have an atmosphere, even if it did once. So this star doesn't give out as much light as the sun, but what it does do is it gives out about the same amount of X-rays as the sun does. And for us out at Earth, the sun's X-rays are not an enormous problem, but if you imagine being 20 times closer, then suddenly those X-rays do become a bit of a problem. X-rays are not great for life. Also, when this star experiences what we call coronal mass ejections, which are events where some of the material actually leaves the star and goes out into space, that causes on Earth beautiful auroral displays. But for a planet like Proxima Centauri,
that much closer,
then you're going to have problems potentially, because those coronal mass ejections could actually start to eat away at the atmosphere of that planet. And if it experiences enough of those, then eventually the atmosphere could potentially get physically stripped away.
Let's assume that this planet has an atmosphere, and it's a benign atmosphere, it has liquid water. What sort of life do you think could possibly live on this planet?
Well, I think we can fairly safely say it isn't going to look exactly like life on Earth. And one of the things that I think you're very unlikely to see are lots of beautiful green leafy plants. If there is any kind of plant life, it's likely to be a different colour. And the reason for that is that plant life on Earth has evolved to take advantage of exactly the kind of light that we receive from the sun. Now, the star Proxima Centauri is a much redder star than the sun, so it puts out light, much more light in the red part of the spectrum. It also puts out quite a lot of infrared radiation that we can't even perceive. And so that means that plant life on that planet, if there is any, it could look red, or it could even look black or grey.
What do you think the probability is of going there? I mean, there are really exciting projects like Starshot. Do you think we'll have to get there within our lifetime?
I think actually it's possible, and that's the first time I've ever thought it's possible, which is why I'm so excited about this. The thing about Starshot is that, unlike most of the ideas that are thrown around about interstellar travel, there aren't actually any hard theoretical barriers to doing that. It is theoretically possible. It's a technological challenge, but it's perhaps of a magnitude similar to challenges we've already overcome as a species.
I can see why you're excited.
Yes.
Well, thank you. That's been fascinating.
Thank you.
Well, Maggie, you're the engineer here. Do you really think this idea of an interstellar probe is possible?
I'd like to think so, but the problem is the stars are so far away, so the technical challenge is quite huge. But looking at the theory, it does seem viable.
It's an exciting solution as well. It's like something out of science fiction. We have a giant laser pushing this probe towards the stars. It's a wonderful story to tell.
It is, and I think it's going to be expensive, but I think it might be worth the effort. Space science is great at doing miniaturization, and this space probe is going to have to be tiny, have an onboard camera, a transmitter to send information back. And so the technology that goes into that can help us all.
Yeah, I suppose if we've got one of these things to go to Proxima Centauri, we can send them to other stars with other planets. We can shoot around the solar system as well. I do find the cost difficult, though. From a scientific point of view, I think there's probably other places to spend the money. But the inspirational value is great. Knowing that that planet's there, it'd be sad if we weren't trying to get there, don't you think?
I think so. I think it's our next door neighbour star. It's got something that looks fairly Earth-like. We've just got to go there, and this seems like a good way of doing it.
Yeah, just knowing the probe is on the way would be so exciting. Well, that's all we've got time for this month, but do make sure you check out the Star Guide, which is on the website.
We'll be back next month with a final update on the Rosetta mission, including the latest exciting images that reveal the fate of the Philae lander that disappeared on the surface of the comet nearly 2 years ago. But in the meantime, get outside and get looking up.
Good night.
Still to come here on BBC4, mind-boggling mapping as cosmologists try to discover just how big the universe is. Stay with us for Horizon next. Then up close with insect life and intriguing transformations with Metamorphosis, the science of change, at 11:30.